Good morning, grade 10. Hope you are all doing well and being safe. This is Miss Pamela giving the physics course. Today we are going to continue the general revision. We already studied electric force and how we can calculate electric force. Today we are going to talk about combining electric forces. So what is the total electric force? The total electric force acting on a given charge is the sum of the individual forces between just two charges at a time, with the force between each pair of charges given by Coulomb's law. So whenever we have several charges near each other, several electric forces exist. If we need to know the sum or the total electric force acting on one charge, we add the individual charges acting on this charge and we can get the total electric force. We find each individual electric force using Coulomb's law, which we already studied. As an example of combining electric forces, consider the system shown in the figure below. Please concentrate on the yellow circle. We have three charges, Q1, Q2, and Q3. If we are talking about Q1 and we need to find the total electric force acting on Q1, we must know that two forces act on Q1. An electric force exerted from Q2 on Q1, and it is a repulsive electric force because Q2 and Q1 have the same charge. And also we have the electric force exerted by Q3 on Q1, and it is also a repulsive force. As we already stated in the previous session, that the electric force acts along the line that connects the two charges. It may be attractive or repulsive. Here it is repulsive because the three charges have the same sign, which is positive. So in this case, the total force acting on charge 1, which is F1, is the vector sum of the forces due to charge 2 and charge 3. So we have the total force acting on charge 1 is the force exerted by 2 on 1 and by charge 3 on charge 1. In order to add them here, we cannot just add the magnitudes of the forces because forces are vectors. They have magnitude and they have direction. So in order to add the forces to find the total force, we need to add them as we add vectors. So electric forces add by vector addition. Electric forces combine by vector addition to give the total force. This addition process is referred to as the superposition of forces. So we do a superposition of forces, which means we add the forces by a process called the vector addition. And I'm going to talk in details about it now. Now look at the figure in front of you where the yellow circle is, to the right. This shows the superposition of forces which I just talked about. It shows how we superpose F13, which is the force exerted by charge 3 on charge 1, and F12, which is the force exerted by charge 2 and charge 1, to find F1, which is the total force. I will explain in details how we add vectors by drawing and by calculation, which we already know from last year, but I will remind you how we do that in order to be able to find the total force acting on a charge and to understand this example more clearly. So recall vectors addition. Whenever you want to add vectors, you add them first by drawing and then by calculation. First, I'm going to talk about the drawing part. In order to add vectors by drawing, you put the tail of the second vector on the head of the first and so on. Then you draw the resultant vector from the tail of the first to the head of the last. So the head is where the arrow is and the tail is where there's no arrow. So you have to remember this rule whenever you are adding vectors by drawing. So repeat it in your head whenever you want to draw a resultant force. You say, I put the tail of the second vector on the head of the first. Then I put the tail of the third on the head of the second, etc. until all the vectors that I want to add are done. And then I draw the resultant vector, which is the total vector, from the tail of the first to the head of the last. We will see several examples. In the figure in front of you, you can see the first two examples. They are very simple because here the vectors are on the same coordinate axis. So in part 1, they both are on the x-axis, or they both are horizontal. So we have 15 newtons to the right and 5 newtons to the left. When I superpose them and I put them above each other, the resultant force is to the right. So it is in the direction of the larger vector. If 15 newtons was to the left and 5 newtons was to the right, then the resultant vector would be to the left. So the resultant vector will be in the direction of the bigger vector. So the resultant vector here is 10 newtons to the right. Now look at part 2. Also we have two vectors that are in the same coordinate axis, which is the vertical. We have 20 newtons upwards and 3 newtons downwards. Whenever we superpose them, So we put them above each other. The resultant vector is the vector drawn from the tail of the first to the head of the last. So it is 17 newtons upwards. It is in the direction of the bigger vector, which is upwards and not downwards. If the bigger vector was downwards, then the resultant force or the resultant vector will be downwards. So we just subtract them from each other. Now in example number 3, we have one vector that is on the horizontal and one vector that is on the vertical. Here we remember the rule that I talked about. We put the tail of the second on the head of the first, and then we draw the resultant vector from the tail of the first to the head of the last. So the second vector is B. We put the tail of B on the head of A, as shown in the figure, and then I draw the resultant from the tail of A to the head of B. In number 4, I have 3 vectors, so it is more complex, but it is easy if we follow the rule. I put A, I draw it like it is, because it is the first vector. Then I bring B and I stick the tail of B to the head of A. Then I bring C and I stick the tail of C to the head of B. And the resultant vector is from the tail of the first to the head of the last, as you can see in the figure in front of you. So this is how we can find the resultant vector by drawing. Now I'm going to talk about how we can find the resultant vector by calculations. So also by calculation, we have to follow several steps in order to find the magnitude and the direction of a resultant vector. First, we find the x and y components of each vector that we need to add. Then you add the x and y components to find the x and y components of the total vector, of the resultant vector. And finally, we can find from these components the magnitude and the direction of the resultant vector. Now follow up with me so you can understand. In order to find the x and y components of a vector, we use the following equations. Rx, which is the x component, is equal to r times cosine angle. R is the magnitude of the vector and theta is the angle of the vector, the direction of the vector relative to the horizontal. Ry, which is the y component, is equal to r times sine angle. So it is the same, but the difference is that here we use sine and not cosine. R is the magnitude of the vector and theta is the angle relative to the horizontal. So in order to find the x and y components, we need to know the magnitudes of the vector, the length of the vector, which are r, which is called r, and we need to know the angle, the direction relative to the horizontal. In order to find the magnitude and the direction of the resultant vector, which will be the last step, we need to use the following equations. R, which is the magnitude, is equal to radical rx squared plus ry squared. So in order to find the magnitude of the resultant vector, we use the following equation: radical x component squared and y component squared. And in order to find the direction, which is the angle of the resultant vector, we use the following equation: tangent minus 1 is into ry over rx. So tangent minus 1 into the y component over the x component. Tangent minus 1, when we want to put it on the calculator, we put shift tangent and not tangent to the power minus 1. Shift tangent, we get minus 1, and then we put the values of the y component over the x component. In order to know the angle of each vector, you follow the rules that I stated in front of you. First, if the vector is horizontal to the right, the angle is 0 degrees. If the vector is horizontal to the left, the angle is 180 degrees. If the vector is vertical and upwards, the angle is 90 degrees. And if the vector is vertical and downwards, the angle is negative 90 degrees. If the vector has an angle other than these 4 angles that I just stated, the angle will be given. So the angle is either given or it will be one of these 4 cases. What is an electric field? An electrically charged object sets up a force field around it. This force field is known as an electric field. So whenever we have an electrically charged object, there is a field around it where it applies its force, attraction or repulsion on other charges. This force field is known as the electric field. Drawing electric fields around point charges. The direction of an electric field is away from a positive charge and toward a negative charge. The stronger the field, the more lines we draw to represent it. So we already talked about this in previous sessions, but I am going to repeat. So whenever we have a positive point charge, the electric field points away from this charge, as you can see in the figure in front of you to the left. Now look at the figure in the middle. Whenever we have a negative point charge, the electric field lines point toward the negative charge. And if this charge is stronger, we will have more lines representing this field. So the stronger the electric field, the larger the number of the lines we use to represent it. The direction of the force exerted on a charge in an electric field. So the direction of the force exerted on a charge in an electric field depends on the field and the sign of the charge. So whenever we put a charge in an electric field, the force acting on this charge depends on two things. It depends on the direction of the electric field and the sign of the charge. If the charge is positive, then the force acting on this charge is in the same direction of the electric field. But if the charge is negative, then the force acting on this charge is in the opposite direction of the electric field. As you can see in the figure in front of you, first look to the left. To the left we have a positive charge with an electric field coming out of the charge. If we put a negative charge in this electric field, then the force acting on the charge is in the opposite direction to the electric field, as we just stated in the previous slide. But if we put a positive charge in this electric field, then the force acting on this charge is in the same direction as the electric field. Now look at the right. We have a negative charge with an electric field coming into it. If we put a negative charge in this electric field, then the force acting on this charge is in the opposite direction to the electric field. But the force acting on a positive charge in this electric field is in the same direction as the electric field. You have just seen the connection between the direction of the electric field and the direction of the electric force. How do you determine the magnitude of the electric field? By definition, the magnitude of the electric field is the electric force per charge. So if a small positive charge experiences a force of magnitude F at a given location, then the magnitude of the electric field E at that location is E equal to F over Q0. E is the magnitude of the electric field measured in newtons per coulombs. F is the force on the charge Q0 measured in newtons, and Q0 is the amount of charge measured in coulombs. So if we know the force acting on a charge and we know the magnitude of this charge, we can know the magnitude of the electric field which causes this force. Now determining the force on a charge. So in many practical situations, you will be given the electric field, so you won't have to find the electric field. You will be given the electric field E at a given location and asked to determine the force a charge Q experiences at that location. In order to know the force that the charge experiences at that specific location, use the equation you see in front of you. F is equal to Q0 times E. So the vector of the force is equal to the amount of charge measured in coulombs times the vector of the electric field measured in newtons per coulomb. And the force is, of course, measured in newtons. This equation gives both the magnitude and the direction of the force acting on the charge. The magnitude is given by the equation F is equal to the absolute value of Q0 times E, and the direction is as mentioned before. If the charge is positive, then the force acting on the charge is in the same direction as the electric field, and if the charge is negative, then the force acting on the charge is in the opposite direction from the electric field. Point charge electric fields decrease with distance. So the electric field due to a point charge decreases with the inverse square of the distance, which is 1 over r squared. In general, then, the electric field, a distance r from a point charge q, has the following magnitude. So if we know what is the magnitude of a certain charge, we can know what is the magnitude of the electric field produced by this charge at a certain distance using the equation you see in front of you. E is equal to K times the absolute value of Q over R squared, where K is Coulomb's constant equal to 8.99 times 10 to the power 9 newtons dot meter squared per coulomb squared. E is the magnitude of the electric field produced by the point charge Q measured in newtons per coulombs. Q is the amount of charge measured in coulombs, and R is the distance from point charge measured in meters. So we can know the magnitude of the electric field at a certain distance from the point charge that is producing this electric field, and as the distance increases, the magnitude of the electric field decreases. Electric fields add together. When a system consists of several charges, the total electric field is found by superposition. That is, by calculating the vector sum of the electric fields due to the individual charges. So, in the previous session, we discussed how we can find the electric field of a single charge. Now, if we have a system that consists of several charges, we can find the total electric field due to these charges at a certain location by superposition. So we calculate the vector sum of the electric fields due to the individual charges. So we add the individual electric fields. This is very similar to what we did when we needed to combine the electrostatic force between several charges. Now look at the figure in front of you. In this figure, we can see two charges, Q1 and Q2. So we have an electric field due to charge 1, and we have an electric field due to charge 2. These fields are represented as vectors in black. These fields can be combined in order to find the total electric field due to both charges, which is the vector represented in red.